Thanks very much, everyone, for joining the presentation, both here and online. My name's Adam, one half of Quicksand 3D, the other half, Shane, I'll introduce to you later. He's from Racecast Engineering. So this presentation is about how to take advantage of 3D printing sand in the foundry industry in particular. So let's get stuck into it. Who are we? So as I mentioned, I'm Adam. So I'm from Hasco Foundry in Ballarat, and Shane's from Racecast Engineering. And we've both been heavy users of the voxel jet, which is a sand 3D printer. And to the extent that we were, I think, 70% of the utilisation of the machine. So when it got to the stage that Cyro had finished with it and it had to transition to industry, it was important for us to try and be able to continue using it and continue provision of the service of sand printing to the industry in general. So we thought, well, why don't we join together and create a company called Quicksand, and that company will continue to provide that service to anyone who wants to use it. So it was very important that we thought we'll put the printer at Shane's site. So the printer's not stored at a foundry, so there's no conflict of interest. I don't need to see what's being printed, nor should I. And it's open to anyone to use. So we didn't want it to be playing favourites towards any particular foundry. So when you're dealing with getting prints done, you'll be dealing with Dane from Racecast, and he'll look after your order. I don't want to spend too much time on what 3D printing is, because I think, generally speaking, people understand it quite well. But there's a picture there of the voxel jet. I'll just turn on my laser pointer. Where is it? Top there. So you can see inside there the build volume of the machine. So it's actually just over 1 metre and 600 wide and 500 high. And you can see in that particular picture, someone's got lots of little cores printing away. Basically, the way it works is there's a big hopper full of sand behind the machine, and in foundries, the sand is a two-part sand system. So you've got a binder and a catalyst. And when you mix those together with the sand, after a certain amount of time, it sets. So in this particular setup, you've got the sand in the hopper is mixed with the catalyst or the hardener, and then it's fed into the machine. And as it comes into the machine will put down a bed of sand, which is 0.3 millimetres thick, as you can see there, the Z resolution. And then the print head will come over the top. It will print binder over that layer of sand, and then it will drop by 0.3 mil. And then you get another layer of sand, and then another run of printing on top. And that repeats over and over until you've printed the whole 500 millimetre height print volume. I've got a video of that here, which is probably not too easy to see in the Zoom meeting, so I might just skip over that quickly. But there's the print head traversing across there. It goes backwards and forwards until the whole print volume is printed. This is a better shot. That's a two-dimensional cross-section. So from there you can see we're printing some impellers. And you'll also notice that in addition to the impellers that are printing, there's a little bit of spare space in the box. So I've got, I think, some valve body cores coming there. And you'll also notice that there's this line around the box. And what we're actually doing is printing the box that we're going to ship the cores in. And that's what protects the cores when we transport them, because they're entirely surrounded by this lighter white coloured sand, which is effectively unbound sand. So you can ship them without the cores moving around too much. And that's what protects them. How much can you fit? More than you think is the short answer. This is an assembly that I printed last week. And as you can see, it's a combination of impeller cores. There's various rail cores that go into little hard castings, a great assortment of different things. And you don't want to waste any of the space at all. And this is quite good, particularly with impeller cores, because they're in open shape. So you end up with lots of space left over, which you can fill with different bits and pieces. Now, that particular print had 895 cores in it. 96 of them were impellers. They're about the size of a dinner plate. That's one of the impeller cores there. Now, this is a quick video showing how it's shipped. So hopefully you can see on the Zoom, it might not be too clear, but basically we ship the box, and then the top layer is only 4 millimetres thick. So you just break it open with your hands, and then you can pull the cores out. And it, as I was saying before, the unbound sand surrounding the cores is what protects them during transport. That's just another example of how they're shipped. So basically, once it comes out of the machine, it's slid onto a pallet, wrapped in protective wrapping. You can see here the little opening that we put in the top, so you can just pop your fingers in and crack it open and extract the cores out. How long does it take? It takes just under 24 hours to print the entire build volume. So it's printing up. So you can potentially print part of a box, but you're printing part of a box in Z height, so you can print upwards and then stop at any height. So if you were to do a half box, it would be a half box in the full extremes of X and Y, but only a percentage of Z. How much does it cost to print a whole box? That model that I showed you from the previous slide, which had all the cores inside, if you were to send us a CAD model like that with everything boxed up, so all we have to do is slide it out of the machine and send it at 2,900 plus GST. If you just need individual cores or a part box or something like that, then just give Shane a call and we'll go over it with you, because we might be able to squeeze it in with another job or position it with something similar size on the other side of the box or what have you to cost it that way. Some commonly heard misconceptions. First one is it's too expensive. $2,900 is expensive, but you can't judge it based on the price. You have to judge it by the value that you get out of the box. I think in that slide that I showed you earlier that had 900 odd cores in it, that averages to about $3 a core, roughly. And that's not outrageous for most cores. And given that 100 of them were those impeller cores, I'd value those probably at about $20 to $30 for an experienced core maker to make, because they're very fragile, they're hard to make. They've got to have core irons inserted, you've got to paint the cores afterwards, and the quality is nowhere near as good, so you're saving time in fettling as well and in knockout. In knockout, I'll just grab one of these impellers. When you knock these out, the sand just falls out, so that casting there was cast using that impeller core that I showed you earlier. You just got to need a gentle tap and all the sand falls out. There's no core irons in there stopping the sand from coming out. So the fettlers find it much easier as well. So there's benefits across the board. It's not just from the moulding and core making side, it's all the way through. Another thing we often hear is it's not proven. Well, we've been doing it for years now and it works really well. In a lot of cases, you get an improvement in quality. It's too risky. There is a bit of risk. You're committing to spending a large amount of money on this print volume and you want to know that the cores are okay. You might have made a mistake with your CAD model and the cores are too big or too small. That's easily fixed by, if you send us a sample of your CAD model, we will often have spare space in the print job that we're running. So we can just pop the core in and send it off to you and you can check that it's all going to work for you first. We've always done it this way. You hear that a lot. I was skeptical too. Initially, we were making these impeller cores by hand and thought there's got to be a better way. And we started thinking about the printing and we thought, it's only 4 mil thick, that core, it's going to break. You can't put irons in there, it's not going to work. And you find yourself talking yourself out of it. But we thought, oh, well, we'll give it a go. And it was fine. And they work really well. If you're not experienced with CAD, that's no big deal. We can help you with that as well. And I want to show you in a couple of slides coming up techniques that you can use to reverse engineer existing tooling that you might already have, because that's another barrier to people adopting it. They don't have a CAD model and they have the impression that, well, we've already got this core box, so why would we swap using something else? And another query we have is, what about chills and sleeves and that sort of thing? Well, chills are fine because in your 3D printed mold, you can just print a cavity and then you can just drop the chill into the cavity. And I've got some castings here, we've done that too, which I can show you later. And the same with sleeves. You just print a cavity in the mold where you want the sleeve to go. It's a little bit trickier with insulating sleeves because they're a bit fluffy on the outside, so you just print the whole oversize and the sleeve will drop in. Exothermics aren't so bad because they're usually more consistent. In fact, there's a mold that we've printed and you can see there's holes in the cope so that the sleeve can actually be lowered in so it's closer to the job. And again, if you can do things like just make the pouring cup the conventional way and glue it to the top, then you're not wasting Z height in the printer. You're only printing what you need to. So what are the advantages? We talked a bit about cost, time, 24 hours. So I've got print volumes that we've printed that have had 1,200 cores in there. And to make those by hand would have taken weeks. The quality is excellent. The cores are porous, and that's important because you don't get many gas problems when you use these cores. The reason being that because the way that the printer works is put down that bed of sand and then it's put glue down. So you've got a random distribution of sand grains making up the core. You haven't got a traditional core where you've rammed the core sand into a pattern and packed it in tight and the cores don't breathe anymore. So when you've got hot molten metal surrounding these cores, the gas off the binder goes inside the core and stays there. It doesn't propagate into the metal. Venting, you're not limited with the design of your core. So you can do elaborate venting to try and help get the gas out that you couldn't easily do off conventional tooling. And that's one of the use cases I'll show you. And the last one there, design limitations, there are less. So that's things like draft angles and undercuts and things that you can do conventionally, but they're a pain, but they're easy with 3D printing. You get complexity for free. The printer doesn't care how complicated your part is. So I thought we'd go through a few case studies and look at a few different parts, and start at the bottom with something really simple like a stick core. And what you often hear people say is they're so easy to make. We've got the core box already. I can make hundreds in a day. The setup isn't that long. It's only 2 halves of a core box. I've got to put in the shooter. That's not so bad. Quality's okay. And why would I do that on a 3D printer? You're supposed to use 3D printers to do these complicated geometries that you can't do any other way. So a stick core is wasted on a printer. And I would disagree with every one of those. The reality is, yeah, they are simple, which means they're also simple to draw. So if you're looking at adopting this process, they're a great place to start because you've got to just draw a cylinder in it, a circle, and then extrude it, and that's your CAD model. So if you're looking at getting into this, then I'd start with your stick cores and your simple cores first. You can make thousands in a day, depending on what the size of the core is, obviously. But I've got examples of build volumes, which I'll show you later, which have 800, 900, 1,000 cores in there, which would have taken an age to make by hand. Setup is negligible. Once you've got your CAD model, you've got it forever. And it doesn't take long to put your CAD model into an assembly, which you can then print. There's a little bit of time in it, but once you've done a few, you get very quick at it. And I would argue that it's still quicker than the setup on a core shooter, depending on the shooter and the core. The quality is much better. I talked a little bit before about how the cores are porous, so you don't get the gas problems that you get off a traditional core. You don't get joint lines. With the stick core, if you've made it on a shell machine, there might be inconsistencies in the core. So, for example, they might be yellow and underbaked, which is going to be a gas problem potentially. They might be hollow in spots, which might work for you if it's venting, but it might work against you if the core prints are loose and you've got metal that flows in, and then you're baking the core from the inside and out. Venting I talked about, we can do complicated venting, or you can quite easily print a vent straight through a stick core. They're perfectly round, so they're not going to be off joint or some other problems that you're likely to see with a core box. And the breakdown is excellent. Some stick cores, particularly if you do CO2 ones, you almost need a jackhammer to get them out, whereas these break down really nicely. The second case study I wanted to look at was core assemblies, which is where this process really starts to shine. So what we're looking at here is, this is a little bronze casting that we make, and you may or not be able to see, but there's a big blowhole up here, defect in the casting. That's one of the problems. The second problem is this fin is too thin. It's supposed to be 5 mil thick. And we've got problems here with the center boss. We've got flash through there, and it's a really good candidate for printing the core instead. So the existing cores were made using this core box. Nothing fancy, everyone's seen that before. But what happens is it's made hundreds of cores, and or thousands, and as a result, every time that they strickle this face off, they're sanding the wood away. So the cores are now too thin, and that bridge is too thin, which is why over here they're now undersized. The second problem we've got is you have to make the core out of 2 pieces and then glue the 2 pieces together. You can't make it in a single piece because you've got this bridge running through the center. So when you glue it together, you've introduced another problem because you've got potential gas problems with glue. And the other problem you've got is that you've got a joint line all the way through, which you can try and paint to get rid of, but you can't really do much about the inside. And it's just another process having to paint them and glue them. So how could we solve that problem with 3D printing? Let's have a look at this core. I'll just turn off my laser pointer. So this is a current design of the core, except it's in halves. So it looks like that. So it'd be better for starters if it was printed in one piece. So we can easily do that because the printer doesn't care about this geometry inside here. And once it's printed, it's very easily cleared out. You just shoot some air through there and it'll clean that right out. And then we thought, well, what else could we do to improve the quality of the core? So what about some venting? So the next step was to print that cavity through the core. So now you've got a path that you can easily put an air gun on. You can blow all this loose sand out and you're not going to have any problems with gas. And then we thought, well, what else could we do to improve the core? So we decided to put these channels in the end, and these channels connect up to that vent path on both sides. So now all the moulder's got to do is drop that core in vertically, and then in the cope, we'll just drill up some vent holes through where these vents are, and then the gas problem goes away. The next case study I wanted to look at was impellers. We use this for impellers more than we use it for anything else, and it worked really, really well. Part of the reason why it's so good, I touched on earlier, the quality of the inside of the core is excellent. They move just as much water as a conventionally made core. You get hundreds in a box overnight. It would take one of our moulders several days to mould that many cores by hand. And they're a lot easier. You're not worrying about core irons. You don't have any of those problems. One of the problems that we did have was without core irons in there, they're very fragile. So this image on the left that you can see here is a simulation of a core being exposed to the hydrostatic force present from the bronze pushing up on it because it's trying to float. And you can see here on the veins where it's green and then red, they're the fracture points. And when that happens, this image over here, you can see that particular core, the vein is broken and floated out the top of the casting. So I'll talk a little bit about how we resolve that problem later. But first, I wanted to talk about how we reverse engineer the CAD model for this part. So this is the model that we drew for that particular core. It's the same one as the one I showed you earlier on the table. And quite often, when you go to reverse engineer stuff like this, you might not have a drawing, you might not have a CAD model, you don't know where to start. So basically what we did here was, in this case, we did have a two-dimensional drawing. So you can import a two-dimensional drawing and just put it on a surface plane. So hopefully you can see that there. If I just hide the body for a moment. So that green line there is the geometry of the inside of the impeller. So basically all I'm doing when I'm drawing the model is tracing that. You can see it's quite easy to do. So that gives you the two-dimensional, it gives you the shape of the impeller, but it doesn't give you the vane detail. So to do that, I just took a photo and I'll hide the body again so you can see it. So that was just a photo of the core box sitting on the floor. And essentially all you have to do then is trace a line over the leading edge of one of the vanes and then trace another line over the trailing edge, project those curves onto the impeller, create a body that's the shape of the vane and then subtract it away. And then you're left with the core as such. I spoke a little bit about how they were fragile through here. And Shane came up with a really clever way of improving the strength of cores just in localized regions. You don't want to crank up the binder across the entire print, because if you do that, remember the sand in the hopper that's got the catalyst in it, it's already pre-mixed. So if you print too much binder, you're going to oversaturate your available hardener in the sand, and you end up going backwards. It ends up weaker. So what you have to do is trick the printer into printing a little bit more binder in the regions where you want that extra strength. And the way to do that is to take advantage of a known property of the printer in that it prints slightly denser binder on the surface than it does on the inside. And if you can create some very carefully designed geometry and actually print holes inside the model, they become surfaces that it then coats extra material on. And we did a lot of R&D on test bars to figure out exactly what the geometry was. So if you have a weak core in a particular region, then that's something you can approach us about for some help without giving too much away. By zooming here, you can see that geometry there, those little dots. That's how it's done. Go back to the presentation. So that's how we solve that problem. The next one I wanted to talk about is two-dimensional reverse engineering, because this is something that most of you will probably be able to do, because most of you have probably got a flatbed scanner that you use to scan documents. So what I actually did was, I'll just grab the core box. That's the core box for the job that's currently on screen. Pretty straightforward. You fill that up and you've got that cap in the top there, which then forms that region there. And we had this core, and we make hundreds of these at a time. The casting, I'll show you the casting quickly. That's the casting there, and you can see that's where the core sits. It just gives you that little undercut there. And we wanted to use the 3D printer to try and improve and speed up core production process. And it's tricky to reverse engineer this because it's got a curved face, and that's really hard to measure and accurately reproduce in CAD. So what I did was, as you can see from these pictures here, it's got some planar flat faces on it. So I just scanned each one of those and then opened that up in CAD. I'll show you those now. So you just import the scan and then you're basically just tracing it. There's one from underneath, one from the top, one from the side. And if I just grab that edge, you see there that that blue dotted line matches perfectly what the photo did. So, or not the photo, the scan in this case. So it's not as difficult as you think, and I would encourage everyone to have a go at it. And it's, yeah, so much time saved by printing these instead, because they're a good one that can fit into the spare space in the box. The next case study I wanted to look at is reverse engineering from a 3D point cloud. So this was a tractor manifold that we did recently. You can see that's the point cloud there. So that was we used a little 3D scanner. It was actually a handheld one that I bought online. I think it was only $700 or so. And basically you insert that into the CAD environment and set it as the background, and then you're effectively tracing the part from that. So that's the point cloud, which you can see, it's just a bunch, if I zoom in, of tiny triangles. And that's the CAD model superimposed over the point cloud. Now, basically the way I drew this was I treated the center as being accurate, and the real casting, these arms out the side, it actually sagged down. As you can see here, the holes don't line up. So I basically had to get this geometry here from the head that this bolts to, and then work backwards from there. I'll just hide the graphics body. So that wasn't too difficult either. Some of these models look complicated, but really they're just a bunch of extrusions, lofts, and subtractions, and it's not too difficult to do once you have a crack at it. So that's the printed mold, which was generated by subtracting that positive CAD model that was just drawn from a volume, and then a runner system was added. It's down the back here, and it's through. We print location as well. You can print handles in the box. These are the cores that were printed. And that's the finished casting with the before and after there. So you can see on the original one, these are all supposed to be on the same axis, but the two outer ones had sagged down because they tried to weld repair the casting here, but ended up cracking. But that's a great example of what the printer's good at, because if he had gone down the conventional route and got patterns made for that, I don't know, is there any pattern makers here? How much that pattern cost? 10, 15 grand just for the pattern. But to print it, it was only 1/3 of the print volume. So about $1,000 worth of printed sand, plus my time to draw it, which was about 8 hours. So it was a vastly cheaper option than going down the conventional route. The next case study I want to look at is this V12 engine block, which Shane did for Racecast Engineering. And in particular, the important thing about this is that it uses the Campbell method of delivering aluminium to the casting. So aluminium forms an oxide in a molten state, and you can't get rid of that oxide. Once it's in there, it's in there. And when you pour the aluminium and you have it tumbling over itself, you're folding those oxides into the metal, and they end up inside the casting. So the best way to avoid that is using this Campbell-based approach, where you have this basin up the top, which you pour the metal into, and there's a plug that blocks the hole at the bottom until you've got metal filled up in the basin. Then you pull the plug out and the metal rushes down underneath. You get the bad, fast-moving metal, which might have some films in it, stuck in this spinner at the back. And then you've got good quality metal slowly flowing up into the mould cavity rather than cascading in the side. So typically with a casting, you've got the cope half, the top half of the mould, the drag half at the bottom, and you're gating it in the parting line, which means you've got some metal cascading down into the drag before it gets to the drag level and starts to flow up gently. So this allows you to avoid that completely. And to make conventional tooling that does that would be quite difficult, but it's very simple with the printer. So there's some prints of the mould. I talked a little bit before about how you can print cavities to drop kills in. This is another example of that. You can see these kills along here, which have been dropped in. And that was the finished casting. Again, you can see the chill marks there where we had the chills in the drag of the casting. Quickly show you the model. This model will bring the computer to its knees, but we'll see how we go. So that uses the entire build volume of the machine to print all these parts of the mould. And I'll just hide some bodies here so you can see what's going on. So yeah, you can see the casting inside that mould assembly there, complete with Campbell method to deliver the metal up gently from underneath. And I'll just turn all of the mould off so you can see the finished casting model. So that's what was cast. And I've got a video of the pouring of this mould along with a simulation of the velocity of the aluminium as it was being poured, which I'll quickly show you now because I think that's a good way to get an understanding of the benefits of the Campbell process. We'll just take a second to load up. So you can see on the right, that's the mould prepared, and we're pouring it out of this furnace. So you've got the basin on the top, and we're going to fill the basin up with metal and then pull that plug out. And you'll see the simulation running at the same time of that happening. So pull the plug, the metal's now flowing into the bottom of the mould. And the idea is you want the metal speed inside the cavity to be as slow as possible, preferably below 0.6 meters a second, which is purple. So we're well under that here, which is what we're trying to do or achieve with this mould, so that you haven't got all these. You can see the biofilm starting to form on the top of the pouring basin here. So the idea of using this method is you don't get all of this rubbish going down and into the casting, which is really easy to do when you can 3D print the moulds and create these elaborate runner systems. So I might just throw it over to Shane briefly. He designed this particular casting, and he can talk to you a little bit about how he went about it and his experience with 3D printing.
Right, not quite sure what I'm going to talk about. Adam's covered a lot of it there. Yeah, basically with the CAD model, with the V12 block, 3D printing became evidently the best way to manufacture this because of the methoding system and a heap of little tricks that we could add to it to make a good quality casting. It's a big expensive casting, and defects are expensive, particularly when you find them further down the track. So yeah, with what tricks we could add, chills, chilling bars, chilling pins through that area there to help chill areas locally. We've actually got two different engine blocks here where we had different chilling systems. We have chill pins, which is very easy to add when you're 3D designing something. There's the chill bars through both the cam tunnel and the crank tunnel. Yeah, the Campbell methoding system, we could put a very, we printed a line in the pouring basin, so that it's basically Adam's job to, when we were pouring that block, to keep the metal at that line. So that's a good guide as well to keep everything consistent with the Campbell methoding system. Yeah, spinner at the back was very, yeah, hard to do any other way, I suppose. Not sure what else there is. If we got other slides here, do we want to on the V12 or?
There's no, just
yeah. No, sorry. What else can we do in 3D printing? We can put. We've got some cooling and flow assist bars down the side, which we've done. If we can see here, inside the water jacket. It's not the best texture to view, but there's actually ribs right through there, and you can't do that any other way than 3D printing. So that assists in the thermal conductivity. Yeah, yes, 3D printing. Other, yeah, these are two components. These are for another foundry that were previously gluing, making these complex little cores. They're basically a U-turn inside and a outer shell, and they're all glued together. They take about 4 days to make 100 of those, and we're looking at, I think we'll get 100 printed cores into a half a print box, so that's about $1,500 to save 4 days work. No glue, excellent venting, perfect geometry every time. As you guys would know, when you glue things together, they never come out the same, never come out perfect every time. And we haven't done this yet, but we will put some venting holes through here that as Adam showed earlier, just to help get a bit of, you don't even have to blow them out. The unbound sand will help vent any gas generated off the core, will come off and out of the mould very easily. Yeah, so that's one of our customers is doing. Not sure what else there.
Show some assemblies.
Yes, yes.
All
Assemblies, yeah.
Thanks,
I'll
Sean.
let you. No, thanks, Adam.
So now that we've seen a few examples of what you can do, I thought we'd take a bit of time to show you some assemblies that we put together so you can see how we pack some of the cores. So I'll just post some of these so we're not bogging the computer down too much. Okay. So this particular assembly I thought I'd show because it was the one that we did most recently, and I've got examples of some of the boards here. So I'll just open that one up. Okay. So we have a CAD model that's transparent here, surrounding all of the cores. That's the actual box that the cores will be shipped in eventually. So we can provide you with that CAD model, or you can draw your own if you're not using SolidWorks. And you probably look at that and think, wow, that must have taken an age to draw all those cores in there. But it's not as bad as it looks, because you'll notice here that all these patterns. So if I turn the patterns off, that's all I had to actually manually place in the box. From then on, it's just a matter of repeating those throughout the build volume. So if I go through some of these, that first pattern, copied the impellers across the bottom, and then the second pattern, spaced them out that way, and then the third pattern, just patterned them up. So it doesn't take long at all. And then these remaining patterns are responsible for putting in all the other parts. You can see that core there was the one from the case study that I showed you earlier. Again, don't waste any space. These are simple stick cores, but you might as well put them in. This little core here is actually, I've got one here. It's that core there. And what it does is it puts the holes in this NiHard wear component. So that's another really good use for this printer. You can print cores and get really tight geometry in holes that, and minimize the flashing too, because this core has got sharp edges, and normally your pattern maker is going to make you a tool that gives you filleted edges so that you can extract it from the core box more easily. But the printer doesn't care about that. You can print a sharp edge, which means when you drop it into the mold cavity here into the core print, I haven't fettled this casting, and it's NiHard. You don't want to fettle it because it's so hard, and there's very little flash because the cores fit so well. So how do you fill the build volume? Round cores like these, you can have them almost touching and they're not going to stick together. When you've got large planar surfaces, like the surfaces between these two impellers here, so one's there and the other one's upside down underneath it, in that case you want to allow 2 millimeters of clearance so that you don't get fusion between the parts. And that's really the only guideline. There's no limitations otherwise, other than obviously don't print. You've got to make sure that your cores aren't inside one another. And if you're using SolidWorks, there's really handy tools to help you with that. And I'm sure the other CAD packages can do it as well. This one is interference detection. If you click on that and hit calculate, it says no interferences, but you would get a list of everything that was bumping into another core, which can help you identify where your problems are going to be before you hit the go button on the printer. And the other thing that's good for is you've got this assembly visualization tool, which you can click, and it gives you a quick count of all the things in the box. So there's 528 of those little cores that I showed you for the NiHard. That one is the box. There's 96 impellers in there. There's some bush cores, that undercut core I showed you earlier, and then I had a little bit of space left in this box, so I filled it with stick cores, and that's what that back wall is. So a little bit about the cost. All of the cores in there were 2,900. As I said earlier, the full build volume is 2,900. I reckon I got that value just out of the impellers alone, which was only 100 of the cores that are in there. So 800, 900 cores I got for free, basically, and they came in a day. A lot of people think that this sort of technology is only for low volume stuff and for prototyping or for complex geometries where that's the only way to do it. But 90% of what I print is production stuff like this, because it's so quick, it's so easy, the quality is so good. And there'll be a lot of cases too where you crunch the numbers on how long it takes to make the cores, and you put a dollar value on that, and then you compare that to the $2,900 to print a volume, and quite often you'll find that it'll come out cheaper if you make them by hand. But the problem is you can't necessarily look at the costing that way. The way I look at it instead is, if I make all of the castings that these cores make, there's about $40,000 worth of castings in there, and I can knock them out a hell of a lot quicker. I don't want my moulders wasting time making cores. I need those guys making moulds. If I can get the cores another way and they concentrate on making moulds, then the $2,900 is awfully cheap all of a sudden. Just show you a couple of other assemblies. Just restart SolidWorks, because when you have large assemblies like that with lots of bodies in there, it can bog down a little bit. Oh yeah, that's a good point. Thanks, Alan. If you got questions, pop them in the chat. If you're joined in the Zoom meeting, and then I can't see them, but Gary's gonna rejoin us later and relay some of those questions to me. Have a look at this one. So this is an example of an assembly that's got cores and moulds in it. So as you can see, there's impellers and sticks and various other bits and pieces in there, but also hiding behind here, you'll see this large mould, and that was actually the mould for that tractor manifold that I showed you earlier. So again, most of the tractor manifold job, the cost of it was covered by that manifold, and all these other cores were essentially for free. And lastly, I'll just show you this one because it's an example of only printing part of a box. So all we've got to do is just alter the height of the box down to the height. I only needed this many cores to finish a particular job for a customer. So yeah, you're not limited into printing the full volume. You can just print part of the box, get your cores that way. Questions? You must have some questions. From the floor first, please.
Well, Adam, it's Gary.
Yes, Gary.
There was a question online from White Industries. What's the shelf life of the cores?
Pretty good. I've got cores that are over 12 months. Oh, sorry, I should repeat the question. You mightn't hear it here. The question was, what's the shelf life of a 3D printed core? We've got cores that we've used after 12 months. They do break down a little bit when exposed to UV light. So as long as you keep them in a dark area away from direct sunlight, then they will last indefinitely.
I agree.
Any other questions online?
No, not yet.
Not yet. Any from the
Oh,
room?
hang on. There's one here. They're starting to come in. Hang on, I'll read them out. Carl from Bradken here. Excellent presentation. How accurate is the printer, and have you scanned against the model?
Well, the question was, how accurate is the printer? Extremely accurate. In my experience, everything measures exactly the size out of the printer within, well, a fraction of a mil, I would have thought. The Z resolution of the printer is 0.3 mil. And do you know the XY resolution of the printer, Gary, off the top of your head?
Yeah, it's between 0.1 to 0.2 millimeter in the X and Y.
Yep.
And like you said, you round up or down to 0.3 in the Z.
Yeah, so between 0.1 and 0.2 mil in X and Y, which is perfectly accurate for this. And that's another good thing I should mention too. When you get the geometry so close, you're minimising the amount of flash you got in the casting. You're minimising the amount of time that the fettlers have to spend cleaning it up. You can, generally speaking, we allow 3 mil of machining for the machine shop, possibly a little bit more on a larger casting, but you can get closer with this geometry because it's so accurate.
Got another question from White Industries.
Yep.
With the removal of core irons,
Yes.
are you able to assist with the structural strength of the core as shown in your presentation?
The core, so the question was, is the core going to be, I think this is what the question was, can you approach the strength of a core with core irons in it with a 3D printed core, I think? No, they're not going to be as strong as the core with core irons in them, but they're strong enough. And you don't want them to be too strong by oversaturating it with binder, because then you reintroduce the gas problems that you have with too much binder. Those impeller cores, we used to make those the old-fashioned way, and we might have had a 10 to 20% reject rate on the ones that had a 4 millimeter thick core, because you just couldn't get rid of the gas.
Another one, someone asked, can chromite cores be printed? And I think the answer is not at the moment, and possibly no.
No, so at the moment, the machine is set up to use a graded silica sand. Potentially down the track, we might be able to look at something like that, but for the vast majority of purposes, we're using silica sand.
Yep, and that was the next question, saying silica sand only, and what AFS is used?
Oh, what's the range, Gary, on the AFS?
No, I'm always bad with AFS. I think it's about 75. Anyway, the average, the D50 grain size of the sand is somewhere around 150 to 170 micron.
Okay, so just for the people in the room, Gary's saying about 150 to 170 micron is the grade of the sand.
I can't remember the AFS number. Sorry, I'm bad like that.
That's right.
It's about a 75. All right, White Industries again. Can you use the core in different materials?
Yeah, as in different casting. Oh, sorry. The question was, can we use the core for different materials? I assume you mean metals, cast metal materials?
Don't know.
Yeah, you can.
Yeah.
I've got examples of castings in aluminium, bronze, cast iron, ductile iron, Murray's done steel castings at Beckwith. So, yeah, you're not limited with the material that you use.
Okay. Gabrielle's asking, have you printed any dog bones by any chance and had them tested? I guess she's meaning dog bone sand samples and testing those.
Yeah, so the question was, have we printed any test bars of the sand to see what the sand strength is? And the answer to that is yes. A lot of the research that we were doing into figuring out how to print those channels through the core to improve the strength, we put a lot of test bars, or broke a lot of test bars to test that. Yep.
So it's not actually a dog bone, it's the 3-point bend test, where the sample is, I've forgotten now, 22.4 square by 172 mil long, and you do a 3-point bend on it. And the breaking force is somewhere about 12 kilograms, which ends up being a bending strength of something like 2-point-something megapascals.
Yeah, so Gary's just saying that the breaking strength of the test bars is about 2-point-something megapascal. Any further questions from the chat room, Gary?
No, they've gone quiet.
Good. Hopefully that means we've covered anything. Nothing else from the floor. So the question was, does the complexity of the part that you're printing change how long it takes to print? And the answer is no. Well, very slightly. You might have seen the video where the print head is traversing over the surface, and if it has to do less work traversing, then theoretically, yeah, it's going to take slightly less to print, but it's still got to print all of those layers, and it takes roughly the same amount of time on each layer, depending on what you're printing. So you're still looking at 24 hours for the full build print.
Got a question online, I think it's from Chris Grant.
Yep.
Were filters used at each ingate at the bottom of the engine block that was shown and simulated?
So the question was, were filters used at the ingates on the engine block that was shown? The answer is yes. I'll go back to the picture. So we're talking about these little blocks down here. So basically the mold was printed with a cavity the size of the filter, so you can just drop the filters in. Similar idea to dropping in chills or dropping in sleeves. You just print the geometry you need, pop it in.
Just to tell the audience, the filters are there for another reason apart from filtering.
Yes.
The process of filtering is limited, but it's to slow the metal down. Yep. In a controlled manner.
Gary's just saying it's worth pointing out that the filters, whilst they do filter, the purpose for them in this particular case is to slow the metal speed down so that you're introducing the metal in the least turbulent fashion to the casting to prevent the bifilm formation, bifilm defects. Yep.
No more questions online yet.
And they said that the cores are quite porous. Have you had any experience with putting pellets or?
The question from the floor from Alan was, the cores are quite porous, so do you have any problems with metal penetration and veining? You can, if you've got a really large thermal mass, like a large heavy iron or steel casting, for example. The steam engine example that we cast recently, but it's not really any worse than you would see from a conventionally made mould anyway. The metal certainly doesn't, it will penetrate as a result of veining where the core is starting to fracture, but it won't penetrate under normal conditions. And the surface finish that you get, it's slightly rougher than the surface finish you get from a conventionally made casting, but it doesn't really detract from the appearance because it's uniform all over. And by the time you put it through a blaster, it's often difficult to tell the difference.
Another question from online.
Yep.
Are there any printing or core defects that you're aware of? So printing defects and core defects that you're aware of.
The question was, are there any printing defects or core defects that you're aware of? Yes, sometimes the printer doesn't print perfectly. It might point a mark or a line through a print. If it does, we can pause the print and restart it, or we can just get rid of that print and print it again if it's a particularly sensitive piece of geometry. Some cores, if you do get a defect like that through, you can just glue the cores together and it doesn't matter. Most of the time you don't have a problem. When you do, there's generally a good reason, and the reasons are pretty well understood now that we've had the machine up and running for a while, and we can usually iron them out pretty quick.
Someone's asking, is the bonding system furane? And I guess the answer is yes.
Yeah, the question was, is the bonding system furane? Yes, that's why they're green in colour.
Yeah, it's a bit like the T-model Ford. You can have it in black, black or black. You can have it, the binder system in furane, furane or furane.
Yeah, so the machine's set up to do a furane print. I don't know that it's easily changed, but it works quite well with furane, so we're sticking with it.
Okay, do you have any experience in using furane cores in phenolic urethane?
Yes.
Is that okay?
I'm assuming you're talking about the moulds. So the question was, have you used these cores in combination with other sand systems?
Yeah.
Yeah, we do. In our foundry, we've got sodium silicate, we've got alkaline phenolic, and we've got urethane, and you can combine all of those and we don't have any problem. You can thermally reclaim this material the same as you would thermally reclaim any other sand material. Really think of any other issues that you would likely to run into by using a different sand system. We do it, we don't have trouble.
Kieran has asked the question, with Hasco being a foundry making castings, what confidentiality assurance can Quicksand provide other foundries that their work will be protected from sharing?
Yep. The question was, what about confidentiality? Hasco's a foundry. It doesn't need to see what the other foundries are doing. What about NDAs? That's all fine. One of the reasons why we set the company up the way we did, and we have the printer at Shane's, not at Hasco, is because we didn't want there to be any conflict of interest. I don't need to see what's being printed, nor should I. If you want to deal with Shane, you deal directly with Shane. I have nothing to do with it. I'm merely involved to provide foundry support for people interested in using the technology. I can give them advice about what the limitations of 3D printing are, what the advantages are, how to go about setting up a job box, all that sort of stuff. But ultimately, what the customer prints is what Shane sees, and I don't have anything to do with it. And of course, he or I can both sign NDAs where appropriate. So there's no issue there.
The online questions have gone a bit quiet. I can throw maybe a comment in.
Yeah, I might have to repeat it, that's all, because they won't hear
That's all right.
it. Go away, go ahead.
Maybe another advantage of 3D printing, you talked about the stick core. You don't necessarily have to print the stick core solid. It could be hollow, so there's unprinted sand inside, which would make the knockout even easier.
Yeah, so Gary's mentioned that with something simple like a stick core, you could potentially print a channel through it that, well, it could serve two purposes. One is it could help with venting, and the second is that knockout's a lot easier because you've got unbound sand in the center of the stick core, which will fall away and allow the core to collapse into a cavity basically and fall out of the part much more easily.
No more questions so far.
Oh, we got one from the floor, Alan.
You're obviously still learning about the process with the 3D printing.
Yep.
Process for development of the impeller core. What's the chance that present? What's the time? At this point, how is dealing with
So the question was, what was the sort of time frame and the problems we encountered in developing the localized strengthening technique? It didn't take too long. We basically, we figured that the idea was probably going to work. It was just a matter of discovering exactly what the geometry was to get the results that we were looking for. And we printed a bunch of test bars with different ideas, different geometries to get the saturation of binder exactly right through the part that we wanted to strengthen. And from memory, I think it was test bar 42 was the magic bar, was the best result. And basically that's the pattern that we've adopted. And it was proven in case studies with that impeller. We used to have a fairly high reject rate on that impeller before we did this. And now if they've survived transportation, then they're going to survive being surrounded in molten bronze and have hydrostatic forces applied to them.
how many supply chain issues with the materials?
Another question from Alan was, do we have any supply chain issues with the materials that we use in the printer? This one might be for you, Shane.
The answer is no.
Yeah, so no supply chain issues. It does take, we need to manage our binder to make sure we've got enough. So we use a special imported binder. And sand at the moment, we're looking for a more local supplier because we're currently getting that from Queensland to get the specific grade that we need. But yes, no showstoppers there. Good question. Yeah. Oh, we're not really. Sorry, the question was, are we interested in doing any other material, I suppose, through the sand printer, through the voxel jet? We wouldn't rule it out, but at this stage, no. It's a big job to recalibrate everything to run a different material. But yes, if there was enough volume there, we would entertain the idea. Anyone else from the floor? Stumped us well enough.
I'll just make a comment.
Yeah.
The printed cores do readily take current mould coating.
Yep. That's a good.
Improve their, resist burning and staining.
That's a good feedback from Murray. He does a lot of steel and iron, and painting and treating the printed cores the same as you would a traditional core will prevent your veining and get a slightly better surface finish too, I'd imagine.
Yeah.
So yeah, thanks, Murray. I think all the feedback we've got from everyone that has used these cores has been pretty positive. Had a few breakage issues with some very delicate cores, but as Adam's been saying with the impeller cores, we've been working our way around those and getting on top of any of those sort of issues. And yeah, everyone that's used them seems to see the value in it.
So where did you
we haven't gone further than Newcastle yet. Actually, we may have sent some to New Zealand. I haven't personally, Quicksand hasn't, but I think some have travelled to as far as New Zealand.
Yeah, CSIRO sent to New Zealand.
Yeah, CSIRO, Gary just confirmed that. They did, yes.
Got a question online. They're asking, will the presentation be available on the Victorian page of the AFI national website? I'm sure the Victorian committee will arrange that. And so the answer is yes, it will be. Yep. You can announce that to the room.
Yep, that's, yes, this will be available online nationally. As soon as Gary has it edited.
Right. Kieran's come up with another question.
Yeah.
What is the current printer utilization? Is there much spare capacity for new work? How long before you think you'll need another printer?
That's a very good question. At the moment, it's...
You have to repeat the question to the room.
Yeah, so the question was, how well utilised is the printer at the moment? At the moment, we're probably running similar to where the CSIRO was at, maybe 1 to 2 commercial prints a week. We can go up to 5. So really we're at 20% utilisation. We're looking to expand that now that we've ironed out all of the teething problems with having it relocated. We're starting to ramp that up.
And the final question was, how long before you think you'll need another printer?
Well, when we get up to about 80% utilisation, I suppose. That question really comes down to everyone on the other side of this presentation. As if more people adopt it, we get that utilisation up, we will expand to fill the demand.
Simon Kay saying, an excellent presentation, well done.
Thank you. More to Adam. Lead times are excellent question. We'd like to try and keep our lead times, I'd like to say within a week it would be ready to pick up from a freight depot or delivered to the foundry if it's a local foundry. So we're trying to keep lead times down as much as possible.
Rodney and Peter Phipps are saying great presentation. Well done. Thank you.
Thanks. There.
Somebody said, hopefully us pattern makers don't need to retire for a while yet. You better tell the room that.
Okay, pattern makers don't want to retire for a while yet, hopefully. Look, this technology I've found, I've designed and made patterns that utilize the sand printed cores and traditional patterns. I've done that myself, and I would encourage any other pattern makers to start looking at things the same. They can put the really complicated, difficult core boxes aside, CAD model that, and make the outer casings. The sand, you basically pay for volume. When you pay for volume, you don't want to be paying for a big cope and drag. That's where I see pattern makers really working on making copes and drags, and the sand printing taking over more of the core, the complex cores. So I would really like to see more integration of both technologies.
Sounds good, they said.
That's good. I do have a lot of respect for the old-fashioned pattern makers. They've done very well with the tools they had. So, yeah, well done to them. Hats off to them. Anything else from the floor?
Online questions have gone quiet.
Yep, good. I'll just hand it over. Thank you. Thanks, Adam.
Yeah. All right. Thanks. Thanks to Shane and Adam for an excellent presentation. The thing that the online people miss out on is that apart from the few samples that Adam showed to the camera, there's a table full of samples here, which are excellent and support for the presentation itself. Yeah, there we go. Have a look at the table. For those of us that are here in person, we'd like to thank Adam and Shane for a really excellent, interesting presentation. Well done.
Well done.
So, as we said, this will get put on our website. That'll happen in the next few days. If you have any further questions, please either direct them to myself, or if you have Adam or Shane's contact details, they're on the screen now. You can go through that, go that way. But either way, we'll make sure any questions get to the right people. So again, thank you.